Okay, guys, now it's another challenge time. If you recall, it's not moving. If you recall here, when we say the dimensionality is only about 7, it's 7x in your formula, then 99% of your data are considered extreme data out and then useless to your model. Any of you has ever thought about that? Because we have seen so many engineering formulas, functions, applications that includes more than 7x. And we also just talk about that weather prediction model, that even the first ever model got a 10x. If this holds, how come these models are still working? Now you start to think about that, right? Why? Can anybody tell me why? You guys understand my question and concern, right? This simple example shows that even for a 7-dimensional space or 7x formula, 99% of the data can be considered as extreme data point and therefore not useful. But how come we have so many applications with more than that? Even the first weather prediction model had more than 10x, 10 variables. Why? No, nobody can give a clue? Because here we made an assumption. Data is evenly distributed. Okay. But in most cases, data is not even distributed. Do you guys know what is the most popular distribution in our world? Normal distribution. This is why we call it a normal distribution. Do you guys know originally normal distribution was not called normal distribution? It was called a Gaussian distribution because it was discovered and modeled, framed by a guy called Gauss. We call it Gaussian distribution. And finally, we call it normal distribution because it's so normal. Understand that? And what is the feature of normal distribution? Data points goes to the center. Now you see what's going on here. This is kind of like an endless wall, a fight. The power of cursed dimensionality keep pushing the data points to the corners, but the normal distribution keeps pushing the data to the center. But in general, if you keep increasing the dimensionality, then the force that are pushing them away will be stronger than the force that are holding them. And that is what? That is this. And that is the tipping point. When the force that are pushing data away to the extreme ends is bigger than the gravity, which is normal distribution, that pulling everything back, then we start to see the tipping point of decrease in performance. That's interesting, right? And now another question, why we have a normal distribution? I should use this one so everybody can see that.
Random error.
Random error, that's actually a way for we to describe everything outside the normal distribution. And yes, random error also follows normal distribution. But why is normal distribution? How come everything, most of things is normal distribution? For example, if I just survey 100 students, their GPA, let me tell you, it's normal distribution. The shape is a bell curve. X is their GPA. Y is the frequency, that's normal. If I survey the body weight, that's normal. If I survey the head, that's normal. I survey whatever thing, big chances they are normal. Why? That's another magic thing about how things work in our universe. So let me see this. If you say this is actually X, let's say, and this is the frequency. And this is called a histogram, right? And this is actually something called a PDF, probability density function. It shows the distribution of something. Okay, if I add this one and another, this one, okay? So let's say this is 1 to 6. This is 1 to 6. Does it equal to this? Can anybody tell me? You shake your hands, shake your head, and else. If I have this uniform distribution 1 to 6, the chance to have you 1, 2, all the way to 6 is the same. Now, if you add 2 together, does that mean that the chance for you to have 2, 3, 4, all the way to 12 is also the same? Do you guys play dice? When you throw 1 die, the chance for you to have 1, 2, or to 6, that's the same, right? But if you throw 2 dice, the biggest chance is what? The biggest chance is something in the middle. The shape is actually this. And the biggest frequency is the biggest, appearance of number is actually, what is the number here? Is 24. 24 divided by 14.7. Why? Think about that. In order to get a 2, you must have 1 and 1. But in order to get a 7, you can be 1 and 6, 2 and 4, 3 and 3, 4 and 2, 6 and 1. Right? It's just more chances to give you the 7. If I keep adding, let me tell you, when you add to 7, the result is a normal distribution. And most interesting thing is, if I have this weird distribution called a triangle distribution, I have whatever distribution, I have another weird distribution, I keep adding until I add 7 of such thing, the final shape look like this. This is normal distribution. Why we call it normal distribution? Now, using English, that means whatever thing you are seeing here is determined by many factors, like my body weight. It's dependent by my lifestyle, by my food, by my genes, and my food, my lifestyle, and my genes all follow some kind of distribution. I don't care. But when they come together, the result will always be a normal distribution. And that also means the result will always be some gravity pulling the data points to the center. Make sense? So now once you start to put the pieces together, you start to see the world in a different way. And it's, so many factors are interdependent, involving, forming some things that is so similar, converge to the same thing, and give you the same answer. And you start to understand why machine learning doesn't work here, but it works there, and why engineering works in this way, not that way. That's the basic rule, mathematical rule about our work. Make sense? Okay, so then this is a model I did when I was doing my PhD. When I start thinking everything together, I run a simulation. I try to understand the relationships between the two things. Remember, this model, it only talks about one thing, the dimensionality and the accuracy, okay? But it forgets another thing, which is the samples. If you have a bigger sample, that's the ultimate cure, that's the ultimate solution. You can always bend this curve to the up. So I was thinking, why don't I add the third one? So I added this one. Now, if you see, this is the variable, and this is the performance. And this is actually the offset dimension. But if you see, this one is the cross-sectional view, just one sample of that is exactly the curve you see from the machine learning literature. But if we increase the sample size for a given number of variables, that is always what? Increasing. For a given number of variables, that is always increasing. Make sense? So, but the problem is what? Can we keep increasing this? The answer is no, because it's so expensive. That means you have to deploy more sensors. You have to track the data more frequently, everything. So let's say if I increase, and it's much easier to increase this. You get my point? Because everybody can have a free opinion. It's kind of like when you're working for a construction company, everybody can say, oh, this definitely matters. That definitely matters. Everybody can insert their opinions. So the cost here is very low, but the cost here is much higher. Then we're going some way like this. We always start from somewhere here. We increase that a little bit. When we start to see the decrease, we go this way, and then we go this way, and we go this way. Got my point? We're going this way until this becomes too expensive. We cannot go any further. I call it epistemic wall. We are hitting a wall. If we cannot break that wall, we will see this. Because it hit the wall, there's no way to go. And the people are still pushing you to add more variables. You will definitely see this trend. That is epistemic wall. Make sense? So this is a really simple visualization of what's going on in science and engineering. That if you check the medical science publications, engineering publications, you definitely see for 5 or 6 years, some people, some scholars say, oh, I discovered a new protein can explain this cancer. And that person, oh, I discovered this new method of curing this disease. That is going this way. And then you start to see people try to get more data to support that until they cannot further improve that and more people start to push new knowledge. That is how human knowledge and human science and engineering evolves. How to break the wall? That is the question. And the solution is, now we are back into our original topic, is big data. Now everything starts to make sense. Why we start to collect messy talk instead of meeting minutes? Because we are hitting the wall. We want to understand more. We are pushing that. We are pushing the frontiers. And this side is the curse of dimensionality, and this side is big data. All right. So another side story, unfortunate story about the tension between us and our world is also how precise we can collect. So it's not only about how big the data is, but also about how precise the data is. Have you guys heard about the butterfly effects? If not, you probably have watched or seen or heard about a movie called the Butterfly Effects, right? It basically describes that a flight of a butterfly's wing in Brazil can set off a tornado in Texas. It shows that a small difference at the very beginning can keep building up until it has a really unexpected result. I created this Excel spreadsheet to show that. So I have this curve plotted from this column A. And if you see the formula, this is something called a recursive formula. Recursive formula is also another natural feature of our world, how things work. It's something I output will be the input of you. So you start to build on that to do something. Right? It's kind of like our economic system. I produce something and you build on that. Or I plot some drawing, I send that, you keep working on the drawing. So that's called a recursive function, all right? So you see this A and A prime is the same. The beginning is 0.4, the beginning 0.4. And now, let me change that a little bit. Now observe. That would definitely be considered as something neglectable, right? So if I measure this thing, the density of this thing is 0.4 or 0.000001, it doesn't make any difference to me. I can use 0.4. Can we? After how many rounds? After 22 rounds, your prediction results start to change dramatically. This is butterfly effects. Let's push that. I don't know how much we can push it, but let's add 3 more zeros. Still, that's so different. Have you guys heard about the chaos sense? This is one of the building blocks of chaos sense. It shows that something we think is irregular or total random. This is once again the mathematical foundation of that. That just a very minor, tiny, neglectable change in the initial condition will generate dramatic disasters in the future prediction. So think about the problem we are facing with data, with sensors. It's not even about the columns, the volume of data you have. It's also about how many zeros after that dot. It's also about the precision. We are facing unprecedented challenge in terms of the data collection and analysis. Make sense? So this is actually another very interesting game that our universe is playing with us. And that's actually another interesting story. Actually, at the very beginning of the 20th century, a lot of physics scientists, they believed that all the problems with our universe was solved. Why? Because the Newton laws can picture and predict the behaviors of every particle. And if we know the initial XYZ and the vector of their movement for all the particles in the universe, and everything's predictable, including your fate, including everything, that is just the movement of all the particles. Until we start to see something like this. It's called the non-measurability. You cannot measure anything in the universe. Like, for example, the weight of my phone. Can you give that a number? You cannot, because it keeps changing to some level. The movement of the particles and everything keeps changing. Because of that, we will always face a boundary of predicting what will be going on in our universe, in our world. That is the science part, but for engineering part, if you want to predict the structural failure of this particular bridge, or if you want to predict whatever, like this is revenue of this particular company, even though you have a really big formula with 1000x, and even though you have the sample size to support that 1000 dimensional space, you can still not predict anything because you are still facing precision requirements now. Feeling helpless. And everything pointing to a temporary solution. I don't think this is the permanent solution for us to keep improving, growing our knowledge, but it's only temporary. That there's a curse of dimensionality. There's a desire for precise knowledge, which means we want to add more X to the formula, but also our inability to measure things. A common cure for that would be the big data. So what can we do with big data now? Don't imagine that we can do a lot of magic things with big data. I can tell you the phase where we are in now is still more kind of like a first grade elementary school student. We can only do arithmetic calculation for most cases. And like I said earlier, even calculating the average number is extremely difficult with big data. And this is the one that your video reviewed. This is the big data processing tools, or the word of big data tools. We have something for streaming. We have something for querying. Querying is more kind of like find this particular data for me, that querying. And also for iterations and the learning. We call this learning, but don't imagine this as a machine learning. This learning is more kind of like learn the average number, learn the maximum number, learn how many numbers. Is more of that. And given the functions, we have different tools, and we have 4 major models or mathematical models to support big data analysis. The DAG model, which is a more graphic model. MapReduce model in her video, that's the most popular mathematical model for big data analysis. Graph model and the collective model. And for each function, we also have different tools, or you can imagine them as software packages to use. So for example, if you are using MapReduce model for pretty much like everything, like for querying, for streaming, for learning, then you are using Hadoop. Oops. Then you're using Hadoop. Make sense? And let's say if you're using, if you want to use MapReduce model and purely for querying, and you can have these things to select from, right? And those things are just the names of different software packages, okay? But they represent, at least this thing, they represent MapReduce and also the DAG model, the mathematical method of that, okay? And this is the Hadoop ecosystem. Why Hadoop? Because I have to say the most important part in this figure is here. Although we still have a lot of choices for big data analysis, but this plan probably represents more than 60% of the existing solutions, the most popular. So let's go deeper into the Hadoop ecosystem. So we have this MapReduce. This, you can imagine this is more kind of like the math or the algorithms. Let me put this way, algorithms. Okay, it's the brain. The HDFS, this is more kind of like a hard disk management system. You know, when you guys try to clean your flash drive, you always have this, do you want to use FAT32? You want to use FAT for macros, for MacBook, there's another file format. It's actually just a different way of managing your hard disk. HDFS is the hard disk, right? And we have this Zookeeper distributed collection service. You can imagine this is the Google Cloud, Google Doc, let me put it this way, for data sharing. You know, this is just a different name for the big data community. And Hive is a data warehouse. You can imagine this is your Dropbox for big data. Data streaming peak, you can imagine this is called a FTP. Do you guys know FTP? You know, that was before Google Cloud, Google Doc. Like when I was young, if I want to share some documents with my friends, there was no email. We actually log into something called FTP slash some kind of an IP address. It's actually a server for us to stream data. So you can imagine that is the FTP, big data version of FTP. Or YouTube channel is not a good way to say that, but if you consider it's live streaming thing, that is more for live streaming, right? Now, HOT, this is data mining tool. What is data mining tool? This is more like Excel of big data. So the big data version of Excel, it can help you calculate the most simple functions such as average, maximum, the frequency, those kind of stuff. And we have this data logger, Flume. What is the analog of that? So when you make changes to a Google Doc, you probably can check the history. Or if you use your Google Chrome to browser, you can have the history, right? So this is actually the browser history. Browser history. And the scoop, extract, transform, load. Yeah, that's what? The matrix calculation. Do you guys, computation? Do you guys know that in Excel, you can do some basic matrix calculation, like a matrix multiplication? You select a whole bunch of numbers, you select another whole bunch of numbers, you can calculate, you know, you add those two matrices together, you multiply those two matrices together, that's matrix calculation. Then this one scoop is more kind of like, or there's something like if you copy something in Excel, and when you paste it, you can see transform. Then the original form look like this, it will now look like this. You can turn at 90 degrees. Yes. Believe me or not, for big data, we have a special software package to just realize that a single function to transform things. HBase is the real-time distributed database. Let me see. Yeah, it's Google server. This is more the Google Cloud server. Google Drive, yes. Google Drive. Things like that. Okay, so now what is describing here is one small piece of this big data tools, and this is the ecosystem for that, but it's kind of like now we have the Google Drive, Dropbox, Excel, the hard disk, the YouTube streaming, Excel, the browser history function, and also the transform thing. That's all we have. We just give them different names. Okay. And this is the most, of course, the most important concept because this represents, I think MapReduce can also be considered as OS, operation system. So the hard disk and its operation system is probably the most important, and we want to learn, go deeper into them. Okay, so what is Hadoop? Hadoop is open source project. You know, it's open source project created by some company, by some business, and shared with everybody. It's a framework for reliability storing and processing PB data using the commodity hardware and storage. What that means is you do not need a high performance computer at UF. You can just use a regular clusters of computers to process it. Hadoop made it possible. Before Hadoop, you need a special equipment to do that, okay? And this is actually the hard disk thing I mentioned. And it provides scalable solution. So it provides really strong computation capacity, storage capacity, and I/O bandwidth. So it provides up to 10 gigabit, external bandwidth. The core components include this HDFS, which is the Hadoop distributed file system. That's the H is actually represents Hadoop. Okay. And by the way, just to remind you one again, this is Hadoop. The entire thing is Hadoop. Okay. And HDFS is the most important thing, which is the hard disk. MapReduce is the distributed application processing and control, is the operation systems of that. Written in Java, so the entire Hadoop is the language that uses Java, and it runs on Linux, Windows, Solaris, and also Mac OS. So it's cross-platform. And Hadoop uses this hierarchical and clustered hardware solution. So typically we have this 2 to 3 level architecture, and the nodes here, that's the fundamental level. That's usually the commodity Linux servers, which means if you want to apply this big data application for your business, you can just buy the regular Linux computers to do that. That's the fundamental thing. And usually for a Hadoop system, you have about 20 to 40 such nodes or racks, or 20 or 40 such Linux servers. And the uplink from the rack to this intermediate routers, that's about 10 or 20 gigabit. So which means the data exchange speed here is 10 to 20 gigabit. And the rack internal, which means from this node to this node, is 1 or 2 gigabit. Okay, so they can send data between here. They can also send data, and that's 10 to 20. And the flat fabric 10 gigabit network architecture is being planned at growing numbers of sites, which means what? Which means they also want to increase the bandwidth even between the nodes, and we want to push it to 10 gigabit. So now it's 10 everywhere. Okay. So Hadoop system is a PB scale file system. We are talking about what? So we are talking about PB is what? It's 1 million of TB, right? No, it's 1,000 TB, correct? Let me check that correctly. I don't want to make any wrong statement. It's here. Yes, it's 1,000 TB. Okay, so imagine this Hadoop system is working with more of 1,000 TB of data. And the files can be written, write, renamed, deleted, but this only append only, which means what? Like if you want to add to your data, you cannot cover the original data. You can only, add a new part of data. And when you delete the data, there's no real delete. Actually, what you are doing, just add a label to that, showing that this data is deleted. This is more for the security of your data. We don't want to just mistakenly delete that, because this system is so complex. Any change can be a disaster to the entire system. But we are facing that kind of a problem now, like I mentioned earlier. Where do we put all the data now, right? So that's still a problem. And it's optimized for streaming the reads of large files. And the way it works is it breaks the data into uniform sized blocks. In the video, it mentioned that it's 128 megabit. And then they duplicate that. Usually 3-4 copies of that. So 3-4 copies of 128 megabit. And they send them to the data nodes for reliability. So we don't miss the important data. And exposes block placement so that computation can be migrated to data. So which means it also has a label or table of content to document where I saved all the blocks of data. The client library directly reads data from the data nodes. So the client library is more kind of like the user interface, that the user interface allows you to directly go to the node instead of going some kind of structure and layers of layers. This is how the HDFS looks like. Like I mentioned earlier, you got a rack, and you guys remember each rack is what? It's just a regular Linux server, right? And you have what? You have about 20 to 40 nodes, or 20 to 40 such things. And each green is what? It's a block. And that size is 128 megabit. And you have duplicates of that. And when you are the client, you can directly read data from the rack instead of going other things. And the operation is actually going over something called name node. The name node is actually a metadata or some kind of label to tell this 128 megabit of data about this picture goes to there, and that at least goes there. It's kind of like some scripts. And so your client server, you go to the name node. It's kind of like you want to find that information, you go to the table of content, and then you can go directly to the rack. Remember, I give you guys an example like iCloud, Apple iCloud is actually building the largest data center in Guizhou, China. Then this name node will say, this part of your picture, that 120 megabits, is in that particular server, that rack 021 there, and that part of server is in UK, 034. That is the metadata, the name node. And when you use your phone to check that picture, if you are using iCloud server, you are not storing your picture on your phone. I don't know if you guys know that. It's actually every time when you check your photo, it's downloading that. What's happening is your phone is the client, and your phone is checking this one and just in real time goes to China, get that part, download it, and then goes to UK, get that part, download it, and put everything together. Make sense? That's how we process big data. It's very different than Excel. I want to say that. It's 1P, it's 1000 TB. It split the file into multiple files, and originally each block was only 64 megabit. And we just about 4 or 5 years ago, we increased the size to 128 megabit. And the data nodes are the actual clusters storing the real information, real data. But I also have the name nodes that is more kind of just artificial table of content to tell the client server or your phone where to find the real meat. And also, usually by default, we make 3 duplicate. We make 3 copies of that. Yeah, so this shows that in metadata is records of file address and a memory mapping, kind of like a table of contents. Okay. And this is called the slaves or the operating units. It process the write, read, duplicate, move, and delete operations. So this is more kind of like the Linux server, store information, but also store some functions. And those, of course, you cannot use that Linux server to play video games or check YouTube videos, but that Linux server can do writing, reading, duplicating, moving, and deleting. That's all it does, and storing the real information. Now, this is the picture of HDFS, okay? And the MapReduce is kind of like the operation system of Hadoop or HDFS. It was first developed in 2004 by Google, and then Apache took it over and keep developing that. And now it's actually, this is old Hadoop 3.3.4 version that was still last year. You guys can actually check, the latest version, the newer version. It's kind of like a Windows system. They keep upgrading their operation system. So this is operation system. We keep upgrading that, okay? The key features of MapReduce model or the operation system. So this is the logic of the operation system. It's designed for clouds. So it can manage large clusters of commodity machines, the commodity Linux servers. It's designed for big data. So it basically, it's kind of like our Windows operation system can support FAT, file format or hard disk format. MapReduce supports HDFS, hard disk format, right? We just give them different names, but the logic is the same. MapReduce programming model. So it basically has this map and has reduce. I know this is very abstract. Let me give you an example. This is the stadium. All right. So now let's say we are having this game between UF and Texas A&M. Is Texas A&M still playing UF? Okay, yeah, they are playing. Now, let's say I'm very interested in knowing how many fans are supporting A&M, how many fans are supporting Gators. And now I place this person at the gate, and whenever this is A&M, I click here. Whenever this is UF, I click here. What is the problem? You are going to have a long line waiting here. You just got one person doing just click, 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 click. This is a bottleneck because we only got one processor, and the speed only depends on how fast people move and how fast this person clicks, right? This is the traditional way of data management. Now, if I have these balls sitting in the middle of the stadium, and I have these sitting areas, right? We have different colors of sitting areas. So for each sitting areas, I place one guy, and they are doing this click, click, click thing all together. So this thing becomes in parallel, and this is much faster. So once their clicks are done, they all come to the central guy and tell him this number, and the central guy start to put them together. All those guys who are doing the clicks for each sitting area is called mapper. And they go into the central guy to tell the answer. It's called a reducer. The reducer means we reduce the amount of data. The mapper means I assign those things to process the data. This is MapReduce. So what is map? This is official definition of that. Map means you divide data into segments, or what we call the tuples, right? And assign them with two things, the key and the value. So number of segments depends on the original size. So for example, if you have three files, 100 megabit, 129 megabit, and 256 megabit, how many segments you have? Now this is a quick question based on what we just talked about MapReduce. So for 100, how many segments you have? Just one, because the block is what? 128. So for 129, how many segments you have? You have to cut 2. So 128 plus 1. Even it's 1, you still need another block to store that. So 256. That's 2, correct? And we give them a key. The key is more kind of like your UFID. And the value is the actual data, the actual meat. Okay, so this process is called a mapping. It's kind of like a streaming data, like your picture. Now I just 128 cut ID and actual pixel values. Another 128 cut, and I give ID and everything. And I send them to different servers. And before that, I do what? I duplicate that, and I send them to different servers. And once I send them, I create a what? A name node, the document where I send them to. Reduce is when you use your phone to download that picture. Now this guy starts to be busy. Okay, guys, come on. And they start to say, they get the name node. Oh, this particular duplicate is in China. Let's go there, download that. 128. Oh, this is still 1 megabit. Let's get a 1 megabit. And this 128, or maybe 50 megabit. And you put them together. That's called a reduce. Makes sense? It's kind of like the central guy is calculating all the numbers of fans. And this is an example. I'm saying is, you have this input file, your picture, I cut them. And then this is the map face. I send them to something called a worker. The worker are computers or servers that is doing the assigning thing, following certain rules. And then they also execute what? The write, delete, move, those kind of functions. It's kind of like, hey, I still have some space in my rack. Come send it here. So you move that part of data, so you have space for that part of data. The Linux server is doing that kind of function. Remember that? And then finally, when you try to, ask for that information, you have this reduce process, and the worker will start to call based on the name node, call the pieces and combine them together to generate the output file for you. So for example, we have this simple task, count. Like this is a book, okay? This is paragraph. I want to count how many deers appear, this word appeared in this book. How many beer, how many river, how many car appear, okay? So the first thing is you split them. So basically, let's say those three words, I think I should use this one for the Zoom people as well. So let's say these three words already 100, oh my goodness. Here. Those three words are already what? 120 megabit, 120. So this is split, correct? And then you map. Map means what? You give them the ID. So here, this is the label, this is ID, and you give them the value. And this is the actual meat or the things I want to know. In this case, I want to calculate the frequency. So the value is actually the number of that. And so what I'm calculating here is I'm only calculating how many deers in this tuple or in this segment. And the beer is actually the name of that. It's also 1. And the river is the label of that. It's 1, correct? And I do the same thing. So I got a car. So here we still don't do the aggregation. We just execute the linear process. So let me check. This is a car. Okay, I'm documenting the label car. How many? It's just 1. Okay, 1. This is a car. Okay, this is a car. How many? 1. Okay, 1. And the river. So I just keep doing that for everything. And then I do the shuffling. Shuffling means what? I want to count. So now I want to group them based on the same tag. Make sense? So when I say deer, okay, all deer goes to this box. All cars goes to this box. All river goes to this box. All beer goes to this box. Okay? And finally, the reducing is more kind of like the adding or the calculation, the actual calculation. So it's doing something here. How many beers we have? 2. Okay, I'm going to reduce this one to 2. How many cars we have? 3. I'm going to reduce that 3. This is more kind of like what? Remember the guys that click. Now they're clicking how many A&M fans, how many UF fans, right? So now they got this number. And then finally, they aggregate things together. Now I know beer 2, car 3, deer 2, river 2. That's map and reduce. You would think, why are we doing this? It's so simple to tell from here, but what is the problem is this, right? Then this is not simple. You cannot visualize how many cars in this paragraph. It's not simple, right? Now imagine big data. We're talking about Amazon. We're talking about YouTube. Every minute, we're talking about millions of lines of data. And we just want to calculate the frequency. You have to use this mathematical process doing that. And this process is called what? MapReduce. And that's the operation system. And where all this data is saving is called what? HDFS. And MapReduce plus HDFS plus many other things is called what? Hadoop. Make sense? This is actually the most popular big data system. Okay, so this is a demo video. I think we have talked a lot of abstract things, but now it's to play a demo video for you guys to see how this thing works. But let's take a quick break. Let's come back at 6:35. Okay, 10-minute break. And we will see this real world example. Okay.